Hi friends, in this video we'll discuss about LC oscillations as well as transformers. Consider this simple circuit. When I connect a charged capacitor with an inductor, say first positive charges were on this plate and negative charges were on this plate. This is a charged capacitor. When I connect it with an inductor, what happens? Charges flow, right, and that gives rise to a current. And inductor has a property of opposing the current change. So it should oppose the current change, and it will do it by inducing a EMF, right? So the induced EMF should oppose the current. So what will be the direction of the induced EMF? It should be something like this, right? I mean, this point is at higher potential than this. So that will be the induced EMF, and hence it tries to oppose the current that is going in this direction. Okay, and charges flow. Okay, what happens then? The current gives an induced EMF in the inductor and magnetic field lines are set. So magnetic flux changes, and because of magnetic field inside the inductor, there is some magnetic energy that is gained by the inductor. Are you getting me? What was the initial electrical energy stored inside the capacitor? It is given by half q square by c, right? Where q is the amount of charge. This is the electrical energy stored inside the capacitor. It is stored as electric field lines, of course. Okay. Now, magnetic what? This will be slowly transferred to the inductor as magnetic energy. Are you getting me? And hence the energy is transferred from capacitor to inductor and again vice versa. So these are called as LC oscillations. And you know that the energy stored inside an inductor is given by half Li square, where I is the current through the inductor. This is the magnetic energy stored inside the inductor, right? So my complete energy is just being transferred from the capacitor to inductor and vice versa. So the maximum energy stored inside the capacitor, that is the Q square by 2C, where Q is the whole charge, maximum possible charge, should be equal to half L Im square, where Im is the maximum possible current, right? And what can I get from this? If I know the initial charge and capacitance and inductance, I can find the maximum current that is possible in this case. So this is the formula you can remember. Q square by C is equal to L Im square, where Im is the maximum possible current. And energy gets transferred, right? Let us see how it gets transferred. I mean, let us observe it detailedly. First of all, what happens? There were positive charges here and negative charges here. And say initially there is some current, okay? Not the maximum possible one. There is some current, and slowly because of this current, magnetic field lines are set inside this inductor and charges are reduced, right? So there comes a state where the capacitor is chargeless. All the charges have been transferred, and at that state there will be electric field lines here inside the inductor. So the energy inside this capacitor is zero now, and the magnetic energy is half L Im square. So at this moment the current will be maximum. Are you getting me? Current will be Im. Now tell me what happens after this. Current is maximum, capacitor is chargeless now, but the current is what? Still positive. It will be in this direction only. I'll explain you. Slowly, because of the nature of this inductor, it tries to oppose the current, right? So here it was maximum Im. Because of the property of inductor, it tries to oppose the current, and slowly the current decreases. But it takes some time to decrease, right? In that meanwhile time, the current is still in this direction, positive direction only. Are you getting me? So what happens there? The charges are reaccumulated in this way. Now the positive charges come onto the bottom plate and negative charges go onto the top plate. So this will be the final charge distribution. And afterwards what happens? All the charges get distributed and there comes a state where the current is zero. I mean the capacitor gets charged fully. And magnetic field lines now in this inductor are zero, or in other terms the magnetic energy stored inside this inductor in the fourth case is zero, and capacitor is fully charged again. So the electrical energy will be half q square by C. Okay. And what can we observe from all these cases? The energy is getting transferred from here and there. That's it. Initially, the capacitor had all the energy. While current is getting transferred, the energy is shared between capacitor and inductor. And when the current is maximum, the whole energy is stored as magnetic energy as half L Im square. And inside capacitor, there is no energy. And finally, what happens? This energy is again transferred slowly, and finally, again, this is converted into electrical energy, that is, energy stored inside the capacitor, and magnetic energy is zero. And this state is analogous to the first state, so the cycle repeats again in the reverse way. This is the typical cycle, or these oscillations just repeat. And these oscillations are similar to the mechanical oscillations which you have in the case of spring. Say you had a spring here and mass attached to it. When you disturb this mass, what happens? This mass oscillates right in this way. And throughout this motion, the energy is just transferred as kinetic energy to potential energy and potential energy to kinetic energy. That's it, right? It is something analogous to this situation. For a perfect LC oscillator, the energy is just oscillating between capacitor and inductor forever. But for a practical case, these oscillations just die after some time. You know why? Energy is dissipated. Actually, you know that energy dissipates only through a resistor. We discussed this before, not through an inductor or capacitor. So, for a perfect ideal case, there should be only this inductor and capacitor. I mean, we are assuming that the circuit or the wires with which this circuit is made have zero resistance. This is the ideal case. So energy is not dissipated in an ideal case, and hence you have oscillations. But what happens in practical case? The wire with which the inductor is made and all these circuits are made, that wire has some resistance. So with that resistance, through that resistance, energy is dissipated, and slowly all the energy is spent away and oscillations die or they're damped. Now you may ask me that is it possible to maintain these oscillations if I build a circuit with really zero resistance? Actually, even if you build such a circuit, even then the oscillations are going to die, because there are many ways to transfer energy, right? To dissipate the energy. Not only through the Joule heating, but energy may be dissipated like through this radiation, electromagnetic radiation, waves. So energy is spent away. So even then, for a practical circuit which you make, these oscillations won't last forever. They are going to die. However, let's move further. Our next topic is transformer. Transformer is a device which is used to convert voltages from higher to lower and lower to higher. And this is a typical transformer which you see. This is the primary or input voltage, and this is the output voltage. Transformer works on the principle of mutual induction. Observe this. Let the number of turns for coil 1 be Np, N primary, and number of turns for coil 2 be Ns. Okay, and the initial voltage, the primary voltage, be Vp, and Vs be the output voltage. Now observe that by Faraday's law, my Vp, V primary, is nothing but minus Ns d phi by dt by the Faraday's law, and this is due to the change in flux, right? Magnetic flux. And the concept here is magnetic flux is changing, and the same flux linkage is for both these coils. That is the concept. The flux linkage is same for both the coils. Of course, you may achieve that in a different way also. Say if both the coils are wound on a same rod, then what happens? You can achieve through that also. Say here you have input voltage, and I want a second coil on the same rod with different number of turns, of course, and here I can have output voltage. Yes, this also works. The concept is you should have a same magnetic flux linkage, and this is possible either by using this arrangement, or you can wind both the coils on the same rod as well. So my V primary is nothing but this one, Np d phi by dt, due to the change in magnetic flux. And similarly, output voltage can be what? Ns d phi by dt. Since the d phi by dt is same for both the coils, that is the concept of transformer. So the Output voltage and input voltages are given by the ratio of their number of turns. You got me? When I divide these two equations, Vp by Vs is nothing but Np by Ns. This is the golden equation. So my output voltage, which is nothing but Vs, is given by Ns by Np into Vp. By controlling the ratio of number of turns, I can manipulate the output voltage. If the number of turns of second coil are more than first, the voltage will be increased, right? And that is called as a step up transformer. You are increasing the voltage. If the number of turns of secondary coil is less than the primary coil, then the voltage will be reduced. That is called as step down transformer. We have made some assumptions here also. We assume that the flux linkage will be same for both the coils, which is what not true in practical situations. However, a typical transformer can give an efficiency of 95% if well built, and that is very good. And if it is 100% efficient, then our formula would have been P is equal to IV for power. Let's assume it is 100% efficient, and so the primary current into the primary voltage should be equal to secondary current and secondary voltage. So what can I get from this? IP by IS should be equal to Vs by Vp, which is in turn equal to Ns by Np. You can remember this. Observe this. Vs is given by Ns by Np into Vp, right? But the current secondary is given by Np by Ns into Ip. So what can we observe? In a step-up transformer, if the voltage is increased, the secondary current is going to decrease. Observe that. So in a step-down transformer, if the voltage is going to decrease, the secondary current is going to increase there. And don't forget that these formulas work only for transformers with 100% efficiency. But however, in practical situations, we have energy losses, right? And they can be due to flux leakage or resistance of windings. Here we assume the primary resistance and current are small. Of course, we also want the secondary current to be small. I mean, the secondary voltage, we take it like this, right? This is Vs. This should be actually open circuit. Then our formula works perfectly. Or if you want to approximate it, it should at least be connected to a very, very large resistance. This is one more assumption we made. And other effects can be because of eddy currents and hysteresis, there can be some energy losses. And that's it. Let's end this chapter. Our next chapter will be electromagnetic waves. Keep watching. Bye.